In this video, we continue with our concepts from Chapter 4, focusing on oxidation-reduction reactions, or what are also called redox reactions. An oxidation-reduction reaction involves two species. One gets oxidized. An element or a compound that is oxidized loses electrons. The other species undergoes reduction. The element or compound that undergoes reduction gains electrons. A redox reaction involves electron transfer from one species to the other. You've already seen redox reactions, so they'll be familiar for you. We just didn't describe them as such. So if we take a metal and a nonmetal and react it, we very often form an ionic compound. So magnesium will react with oxygen. Magnesium is a group 2 alkaline earth metal. Oxygen is a chalcogen. Magnesium loses 2 electrons to the oxygen. Magnesium becomes magnesium 2 plus ion. Oxygen becomes O2 minus. We form magnesium oxide. That is a redox reaction. Magnesium is oxidized. Oxygen is reduced. But there are other reactions, including some covalent compound reactions that we also saw earlier, and they are redox reactions. So, for example, molecular hydrogen, H2, can react with molecular chlorine, Cl2, to form HCl, hydrogen chloride. In order to discern if we have a redox reaction occurring, we use basic rules where we assign what we call an oxidation number. What is an oxidation number? Well, it's really a bookkeeping tool. It's not an exact number, but it is an integral value that will, generally an integral value that will apply to atoms within a compound or within a polyatomic ion to account for the electrons in a system. So the oxidation number is really just a formalism in a sense, but it's a bookkeeping tool that works very well. And so the oxidation number can be visualized as follows. If we look at the first 3 rules, this will hopefully help us to understand this. If we have an atom in its elemental form, whether it's a monatomic element like argon, or if it's a metal like sodium, or if it's a molecular element like oxygen or chlorine or fluorine, the oxidation number is always 0. And you'd expect that. We would expect the effective charge on the atom to be 0 because the electrons are truly shared evenly. For a monatomic ion like chloride, Cl minus, or sodium ion, Na plus, the oxidation number equals the ion charge. The third general rule, the sum of the oxidation numbers for all the atoms in a compound add up to 0. The sum of the oxidation number values for the atoms in a polyatomic ion add up to the ion's overall charge. So, in perchlorate, ClO4 minus, the oxidation number of chlorine plus the oxidation numbers of each of the oxygen atoms would sum up to equal -1. Since that is the charge on perchlorate ion. These general rules hold for all systems. Now, the lower rules are rules for specific atoms or periodic table groups, and these generally hold, and they'll hold for all the systems that we will look at. For group 1, the oxidation number equals +1 in all compounds. So for lithium, sodium, potassium, and so forth, their oxidation number is +1. For group 2, beryllium, magnesium, calcium, strontium, their oxidation number is plus 2. For hydrogen, the oxidation number is plus 1 whenever it's combined to a nonmetal, like hydrogen chloride, or it's minus 1 when it's combined with a metal or with boron. So sodium hydride would have hydrogen as minus 1, the sodium is plus 1. Fluoride is negative 1 in all of its compounds. Oxygen is usually negative 2, except when it's bound with fluorine, in which case it takes, fluorine is always negative 1, and oxygen will have whatever it needs to balance out the compound. And then for peroxides, the oxidation number for O is negative 1, and a peroxide is O minus. And group 17 is generally negative 1 when any group 17 element is combined with a metal, a nonmetal accepting oxygen, or with another halogen that is lower in the group. And we'll see some examples of this later on. So we'll do some oxidation number assigning in our next video. So here's a summary of the idea of a redox reaction and the terminology that we use. So in this case, X might be a metal and Y might be a nonmetal. The electron shifts from the metal to the nonmetal. We would say that X, the metal, loses electrons. X is also, we say it's oxidized. It is the reducing agent since it reduces Y. X increases its oxidation number. So it goes from a value, maybe starts off at 0, it becomes a more positive value. Y receives the electrons. So we say Y gains electrons. We would say Y is reduced. Y is the oxidizing agent since it's taking electrons from X and it's making it get oxidized. And Y experiences a decrease in its oxidation number. It becomes less positive or more negative. We're going to look at 4 common types of redox reactions. The first is a combination reaction. Anytime 2 or more elements combine to form a new compound, that's a redox reaction. A decomposition reaction. This is the reverse. Anytime a compound decomposes to form 2 or more products, and we'll look at this primarily with elements, that's a redox reaction. Displacement reactions. So there are single displacement reactions, like X plus YZ goes to XZ plus Y, and we'll see some examples of that. And then there are double displacement reactions, where there are switching of partners within the reactants. And finally, there's combustion. That's the process of combining with oxygen. So here we see combining elements to form an ionic compound. This is a combination reaction. So if we look back above, our combination reaction might be a reaction with 2 elements. So we can take, for example, potassium and chlorine. We mix them together. They react pretty violently. They give off a lot of heat and light, and we form potassium chloride. Initially, potassium has an oxidation number of 0, and so does chlorine. They're both elements. In the final compound, potassium has an oxidation number of +1, chlorine is -1. Next up, we're going to look at a video, and this is taken from our research laboratory. We look at nanomaterials, and we particularly have been looking over the last decade at nanometals, using these for propellant applications and hydrogen production and other things. But we're going to see that these can be very energetic processes. And so we're going to look at a reaction where we have approximately 25 milligrams, that's about 1 match head worth of material that's exposed to air. So this is aluminum reacting with oxygen in the air. As soon as it hit the air, you saw the huge flame shoot up. Hopefully you didn't notice that they weren't wearing safety goggles. When you get into lab, you will wear safety goggles. It turns out this is one of the most energetic reactions that is known. It's a thermitic type reaction. The material has a very high energy density. But you can see that was a simple redox process. In fact, if you ate breakfast this morning, you use that food in a redox process from which you derive all your energy. Next up is decomposition of a compound. And in this case, the example is mercury 2 oxide, so HGO. So this is the reverse of a combination reaction. This is a decomposition reaction. So if I have HGO, I know oxygen has a oxidation number of -2, therefore mercury must be +2. But if we heat this material, then metallic mercury is released and oxygen bubbles off. And the mercury, of course, is an element, and so its oxidation number is 0, and so is oxygen's. O2 is 0. Here is a displacement reaction. An example of a displacement reaction would be lithium's reaction with water. Lithium or sodium or any of the alkali metals react with water violently, and they produce hydrogen gas. So if you think of a water molecule, the hydrogens there can be displaced by the metal. And so if one lithium atom comes in and kicks out a hydrogen atom from water, and a second comes into a second molecule, then we form two molecules of lithium hydroxide, and the two hydrogen atoms combine to form H2. And that middle picture up above, you see the bubbling from the hydrogen gas. And in fact, you can ignite the hydrogen gas off of this that you release. You can do the same thing with nickel. If you react nickel with an acid, like HCl, the nickel can displace the hydrogen from the chlorine, and the hydrogen gas comes off, and we have nickel chloride produced. You can see nickel increases its oxidation number, it's oxidized. The hydrogen decreases its oxidation number, and it is reduced. So acids, as we learned earlier, acids give off H+. So acids, they're acids and they react with bases, but acids are also oxidizing agents. Here we can see a metal displacement reaction. So we have copper wire and silver nitrate. Turns out silver is a very stable metal. And so if I have silver nitrate, that's silver in the oxidized state, silver can come in and displace copper and release copper ions. And you can see this in the bottom reaction. Silver nitrate plus copper produces copper nitrate plus silver. Silver went from +1 to 0. Copper goes from 0 to +2. The copper is oxidized. The silver is reduced. You can see the blue color of the copper aquo complex in the right-hand panel. Now this table here is one that you should print out because you will use this later on when we solve some problems. This is what's called the activity series. The activity series identifies how reactive a species is in a redox sense. So the elements at the top are the most reactive, and the elements at the bottom are the least reactive. So at the bottom you see gold and silver and mercury. Not all the elements are on here. If platinum was on here, platinum would be at the bottom as well. And at the top we have the most reactive metals like lithium, potassium, and so forth. So these are highly reactive metals at the top, alkali metals and alkaline earth metals. And in looking at these, the metals at the bottom will tend to stay in the metallic state. The metals at the top will tend to go to the ion state. And we'll see some examples on how we use this table later on in reaction prediction. Now let's look at balancing redox reactions. You learned how to balance reactions back in Chapter 3, but for redox reactions we have special rules. If you simply balance by inspection, you can often get multiple different answers for a redox balancing process, and some of the answers will be incorrect. In order to balance redox reactions, we need to balance both the charge as well as the atoms. So the approach that we use to balancing redox is shown here. First, we determine the oxidation numbers for all the species in our reaction, and we identify which ones are undergoing reduction and which ones are undergoing oxidation. Then we split that reaction into two half reactions. In order to do that, we take the species that is undergoing reduction and we make a reaction for that. So we have the oxidized form and then the reduced as a reactant and the reduced form as a product. And then we take the species that is undergoing oxidation and we make a half reaction for that. We take its reduced form as a reactant and its oxidized form as a product. Then we take each of these half reactions and we balance them with respect to atoms and with respect to charge. In order to do this, we start off and we take one half reaction and we balance its non-oxygen and non-hydrogen atoms. Next up, we balance the oxygens by adding water, and then we add protons to balance out the hydrogen atoms. At this point, for that one half reaction, all the atoms will be balanced, but the charge on each side will not be equal. So the charge on the product side will not equal the charge on the reactant side. So you will need to add electrons to one side only to balance out the charge for one half reaction. If you have an oxidation half reaction, you will have to put the electrons on the product side. If you have a reduction half reaction, you'll put the electrons onto the reactant side. Now, you do this for the second half reaction, and each of the half reactions will be balanced with respect to atoms and charge. Now, before you add the two reactions back together again to give us our net reaction, you multiply each half reaction by an integer if it's needed to make sure that the electrons on the product side of one half reaction is equal to the electrons on the reactant side of the other half reaction. That way, when you add the reactions together, the electrons will cancel, and then you cancel any identical products on each side of the reactant product side to give you your net reaction. We'll do a series of examples with this in our next video, and you'll need to practice this on your own to see how this works out. The final thing we'll mention here, we will do no calculations with this. We'll simply mention the equilibrium state. We've drawn reactions going in one direction. I may take lead nitrate and potassium iodide, add them together, and I get lead iodide solid. But it takes a moment to look at this, but if you throw pure lead iodide back into water, small amounts of lead will actually dissolve back into solution. That's what's called an equilibrium process. Reactions can go in both directions. So for example, here in this picture, you have calcium carbonate, you heat it, you form calcium oxide, and CO2 comes off. But if you seal the vessel up, some of the CO2 that comes off can react with calcium oxide and reform calcium carbonate. This is an equilibrium process, and you will study this in a lot of detail in general chemistry too.